In this video, we will discuss bipolar junction transistor operations. So continuing our discussion from the previous video, where we defined and calculated the base transport factor, alpha sub t, and the emitter injection efficiency, gamma, the total effectiveness of carrier injection from emitter through base and into the collector can be characterized by the product of these two factors. And this we define the product of alpha sub t and gamma as a new parameter called alpha, to be denoted as alpha sub f. And then from the Kirchhoff's law, the summation of all these currents, and these currents, base, emitter, and collector currents, are defined as a current coming into the device. So the summation of all this should equal to 0. And the emitter current is related to the collector current through this new parameter, newly defined parameter alpha sub f. So including that as shown in this equation, we get a new equation that relates the collector current to the base current. And the proportionality constant that relates these two current components is related to alpha sub f, and we define this new parameter alpha sub f divided by 1 minus alpha sub f as beta sub f. The quantity alpha sub f and beta sub f both define and represent current gain. Particularly beta sub f represents the current gain between the base current, which is often the input current, and the collector current, which is often the output current. So in a typical bipolar junction transistor, the parameter beta sub f is of the order of 100, and the alpha sub f is a number that's very close to 1. So here are some examples of the bipolar junction transistor in an actual circuit. The left shows the something called the common emitter configuration, where for a given input current into the base, so I sub b here is the input current, and then you monitor the output current, which is the collector current here on the collector terminal, as a function of the voltage that you apply on the collector. So if you do that, then you get this collection of IV curves as shown here in this figure, in this plot. The main point is that as you increase your IB, the base current, the collector current increases, so it goes up as you go up in this plot, and that ratio, the collector current to the base current, is represented by this current gain parameter beta sub f. On the right here, you have a slightly different configuration. This time, you monitor the collector current as a function of the emitter current. Emitter current in this case is the control current or input current. This configuration is called the common base configuration. Again, as you change your I sub E, the emitter current, you change your I sub C, and so I sub C increases as you increase I sub E, and that ratio, that relationship between I sub E and I sub C, is represented by the parameter alpha sub f defined in the previous slide. Now, just to sum up the active mode operation, which is the operation that we have discussed so far, the active mode is the case when one junction in BJT is forward biased and the other junction is reverse biased. When the base emitter junction is forward biased, it's called the forward active mode. When the base emitter junction is reverse biased, then it's called the reverse active mode. If the device is perfectly symmetrical, in other words, the doping densities in the emitter and collector regions are the same, and also the base region doping is uniform or symmetric, then, of course, there is no difference between the forward and reverse active mode. In most cases, in real devices, usually the transistor is designed to operate in the forward active bias, and the doping density is not uniform, the device is not uniform. Usually the emitter doping density is much greater than the collector doping density, and also the base doping is non-uniform. Now, we talk about transistor switching now. So for switching operation, the transistor is operated in saturation mode or in cutoff mode. So in saturation mode, both junctions, both PN junctions in the BJT are forward biased. So as shown here in the diagram down here, the emitter injects minority carriers into the base. So electrons are injected from emitter into base. At the same time, electrons are also injected from collector to base as well. So that leads to a very large increase in the minority carrier concentration in the base region, and this represents an on state for this transistor. Eventually, in order to switch this off, you have to pump out the accumulated minority carriers in the base region, and it takes time. And the time it takes to pump out all the minority carriers is one of the limiting factors in the switching speed of this bipolar junction transistor. Now, the off state of the transistor is cutoff, which is the state where both junctions are reverse biased. So in that case, the minority carriers in the base region here are pumped out into emitter and also into collector. So the minority carrier density in the base region decreases, reaches almost zero. And the transistor in this case passes no current, acts like an open circuit. Even though there are really no current flows in the device, this state represents the increase of depletion region on both emitter base junction and the base collector junction. So that change in space charge region requires a flow of a displacement current. So this transistor behaves like a capacitor, much like the reverse biased PN junction, and switching these transistor from this off state into on state requires some flow of displacement current in order to reduce the built-in charge in the space charge region in these two junctions. So here is a very simple circuit involving a bipolar junction transistor. Emitter, this configuration is called the common emitter configuration. The emitter terminal is on ground and your input voltage is fed into the base terminal, and the output voltage is taken off of the collector terminal, and your collector terminal is connected to a load and eventually to a power supply. So if you plot the transfer characteristics, which means the relationship between input voltage and the output voltage, input voltage again is a base voltage and the output voltage is a collector voltage, you will see that at very low input voltage the device is in cutoff, and very high input voltage the device is in saturation. In between, the device is in active mode. So when the transistor is used as an amplifier, then the transistor is typically operated in the active mode region. But for switching operation, the transistor is switched between cutoff and saturation. So in this very simple geometry, this transistor circuit acts like an inverter, digital logic inverter. So low input results in high output, and high input results in low output.